Paolo TECCHIO, PhD student at the University of Bochum. Daniel Han Lab. Han was quite good, the pronunciation. Ah, fantastic, my German is improving. Concentric versus eccentric. Concentric going uphill to 8,000 meters, eccentric going downhill. Does how we train shape what we gain in 8 minutes? Go ahead.
Thanks, Gaspar. So why we ask, does how we train shape what we gain? So everyone thinks concentric training results in different adaptation than eccentric training. But you might be surprised to know that till today there is no randomized controlled trial, as pointed out by Lavori recently to a commentary, to actually Martino. And actually there is no one that mechanically match the two training modalities. But before moving to that, because we did it, let's introduce the setup we use. So we had a control group with 10 subjects and a training group with 13 subjects that perform contralateral training. So one leg performs eccentric training, the other leg concentric training, randomized. And this is the setup, so with the foot attached to the dynamometer, which every time control the kinematics. And we did 2 evaluations, pre and post, with 8 weeks training between. And during the evaluation, we also had an ultrasound transducer over the tibialis anterior muscle and a bipolar EMG. So we focus on the dorsiflexor muscles, and particularly on the tibialis anterior muscle, which is the main dorsiflexor, that contributes up to 50% of the total. So this was the setup for the training and for the evaluation as well. For the training, the range of motion we select went from 5 degrees dorsiflexion to 40 degrees plantar flexion over 3 seconds rotation-ish. And importantly, we use a torque angle time match strategy. But what do we mean by that? So here is active torque over joint angle. So this is the torque you generate voluntarily. And imagine you start from 40 degrees plantar flexion, where the blue arrow is, and as soon as the rotation starts, imposed by the dynamometer, you start contracting, so you go right to left, and you end up in a dorsiflex position. Torque angle time match means now we reproduce the same exact torque, just in the opposite direction. So instead of shortening, our muscle is lengthening. And we have very similar torque, very similar angles, just in the opposite direction. And this results in matched torque, external joint torque, as well as the internal fascicle force or fascicle length change, as you can see here. So we used this strategy to match the training, and we were successful in that. As you can see here, we have the outcome of the 2 training. I will tell you which one is which, so we can put some bets on. But what is nice is you can see the active torque over time, and this curve looks quite nice and similar, almost symmetric. And it's basically, you can see week by week, we adjust the training load, here especially the intensity. Basically, we adjust the sets, reps, and frequency. And at this point, we're quite good, so in the end, we collected almost 18,000 contractions. When we planned 18,200, so they stick to the program. And I now move into the first results by talking about the force-length relationship. So here we have normalized fascicle length on the x-axis of all the plots over fascicle force. Normalized for the pre-evaluation, as you can see by the dashed line, and the continuous lines represent the post-evaluation. So starting from the very right graph in black, we have the control group. As you can see, no major changes, luckily for us. In the center, we have the concentric group in blue, and on the very right, we have the eccentric group in green. And you can see there is a vertical shift, so on both of them, so they increase their strength of about 3 to 7% to give you a range, particularly in the short position. And what's interesting is both exhibit a right shift over longer lengths, which is surprising for concentric, as most of researchers claim that there should be a left shift over short length. And this might be because lack of control group in other studies, or different matching strategy, or no matching strategies. However, we know that not only fascicle can adapt, but also connective tissue that maybe transmit force from the fascicle to the tendons, such as aponeurosis. And as well as to the ultrasound, there's also some particular limitations. And therefore, we employ 3D ultrasound as well in this study. For those of you that are a bit unfamiliar with 3D ultrasound, I quickly sum up how it works. So we have an ultrasound transducer firmly attached to a rigid body with some markers that are tracked by a motion capture system. And basically we know the mathematical relationship between the image and the world coordinate system, so with a transformation matrix. And then you can refer where each pixel is in the space in 3D. And you can reconstruct images. And you do a scan, so you glide the probe over the shank to collect images. So we did this at 50 degrees plantar-flexion, 35 and 5 degrees dorsiflexion to cover and span the entire force-length relationship. So for each bunch of image, then basically we segment and we highlight, you can see part of the TA muscle borders, and in red the central aponeurosis. So participants perform also some contractions, so we have muscle force match condition across the 3 different angles. So, and we were able every time to reconstruct the aponeurosis in 3D, as you can appreciate here. So we have an object in 3D where we can estimate some properties. So you can see here we can get the length from the proximal to the distal FDJ, and we can also estimate how large, so the width of the aponeurosis is, represented by the color map. You can see that relatively narrow, it becomes wider where it is red, and then it becomes narrow again. And interesting, for example, this aponeurosis was twisting right at the edge. But thanks to this number, and due to the force match conditions, we can estimate apparent stiffness and some mechanical properties of the aponeurosis as well. And before showing the results, please take them with a grain of salt, because it's n equals 2, as it takes quite a bit segmenting. So first of all, to give you an idea, in green is the 30% intensity, in blue the 60% intensity. You can see we match the same theoretical estimate muscle force of TA across the 3 angles, pre and post. So this allows us to tell a bit more about potential adaptation. And starting from that, you can see that the apparent stiffness of the eccentric group almost doubles, so increased quite a bit, while the concentric group increased slightly. Regarding the geometry, let's say, of the aponeurosis, the control group stayed the same, fortunately for us. The eccentric group got a bit longer, while the concentric group got a bit shorter in the terms of how long the aponeurosis was. While the width stayed relatively similar among all of them, maybe the eccentric group got a bit wider. We still aware that it's still n equals 2. But this is pretty interesting because it looks like the aponeurosis adapted differently, although the force length looks relatively similar in how we change between the 2 groups. So we would like to, and I would like to spend the rest of today talking about what are your ideas, what are your expectations regarding the potential adaptation to a torque angle time max training. Do they adapt differently? Do they adapt the same way? Do they get longer or shorter? Does the aponeurosis adapt like the muscle architecture, or follows more like a tendon, so it cares a bit less what the muscle is doing, cares more about the load and the strain involved. So we would like to know your opinions. But first of all, before opening the discussion, I would like to thank my team, and also Alberto and Gaspar for the invitation. As you know, maybe Gaspar has quite a lot of effort in this. Thanks.
Yes, it's writing email and going up and down the stairs. So now Martino is up there and they will arrive.
Thanks, Martino. Ciao, Paolo. First of all, I think that this study was needed because it's an advancement of what we had so far. So well done to you and to the team to have thought about this study. And it's fantastic to see how you match that, because you know probably you read something from now it's 12 years ago, and we decided to match it for theoretical neural activation, which is had limitations, but it was the best thing that we had at the time to do it, right? So now, like, you go back to the result? This is a little comment, and then I leave to the others to question. To the results for the fascicle lengthening.
For the force length?
Yes, please. Force length, yes. So, actually, you said like this is not what somebody expects, or maybe like not what many people would expect. I would have expected something like this from the studies that I performed with actually 2D ultrasound, so limitations on that. And it's because, like, if you look into the literature, the concentric training often results also like in lengthening of fascicle 2. In this situation, what I see is that there's a broadening of the force-length relationship there, okay, so which is what we see usually with other after lengthening training, okay, which you don't see actually in concentric, although you see a right shift of the relationship. So I'm thinking here, I have two questions. The first thing is good because there are like fascicle lengthening after concentric, so I think that this happens, and I truly believe this data. And second thing is TA the best model to prove this as a muscle?
Yeah, so thanks Martino. I mean, first thing, yeah, I still also doubt about using Solute sound because it's impossible to standardize the location, especially if the muscle change. That location probably doesn't exist anymore. Plus maybe the muscle bulge differently, so it changed the plane of the tracking. Let's say that's nice that at least I have a control group helping me. Regarding the tibialis anterior, it's actually a good model to study because you know it's the main dorsiflexors, it's superficial, so it's also relatively easy to image, to get, as well as it's monoarticular, so it's not sharing its tendon with other muscles. So regarding potential problem with motor redundancies, definitely reduced. So that's why we choose it. And another maybe note, that maybe was out of our thoughts. We said no one trained TA, so probably there are massive gains, but that was not true.
Quick question, last.
Hi Paolo, thank you for your presentation. I was wanted to know if you tried to correlate the changes in the right forward shift of the relationships with some, for example, changes at the level of the ponerosis stiffness or maybe tendon stiffness. So how could you explain these changes, especially for the concentric training group?
Thanks, good question. We still have to analyze all that ponerosis data because it takes ages, and they finished just December after 3 years of collection of data collection. We will definitely check, but from the aponerosis point of view, to some data also made an algorithm that you get 3D fascicle reconstruction of the entire volume, so you can also have regional information. But we still have to analyze because I think 500,000 frames to check that, and as you can see, glasses get thicker, so probably still a long way, but we will definitely check this thing.
Thank you, Paolo, also from the optic that will change your